Note that this video is meant for someone with mathematical knowledge up to an Algebra 1 level, so a lot of simplified concepts will be used. I've tried to make the steps as short as possible without touching all the parts in calculus, but anyways, enjoy the video. Today we'll be looking at derivatives for polynomials and other simple functions, which will eventually lead to the logarithm ln x. This is a fairly beginner-friendly introduction to the definition of derivatives and the general formula for deriving polynomials of degree n. A common way to approach derivatives is as an extension of slopes and lines. In first-degree polynomials, or just linear functions, at any given point, the slope is always equal to some constant, as in 1 in y equals x. Likewise, you can use this rate of change definition on nonlinear functions, such as y equals x squared. So let's start analyzing y equals x squared, specifically at the point 0, 0. On this point, it looks like the parabola as a whole is not moving, or the slope is equal to 0. Of course, it's not actually staying still with a slope of 0, since moving the input left or right just a slight bit of it will result in a slightly larger output. But we can say that at that moment of time, it appears that the point is just moving straight across the x-axis. Likewise, on the point 1, 1, we can say that the graph is increasing and thus has a positive slope. On the point -1, 1, it would instead be decreasing and would have a negative slope. Another way of seeing this is that when we let a straight line continue from a given point, at 0, 0, a quote-unquote smooth line, which continues the parabola, is just a flat line with a slope of 0. On 1, 1, the line which continues the parabola will be a line with a positive slope. Another way to say this is that the growth rate is the same as the slope of a line which is tangent to the curve at that point. Alright, so how do you find out what the slope at 1, 1 is? Well, by zooming. If you continuously zoom into the point on the parabola, the curve looks like it straightens out. So this quote-unquote infinite zooming would lead to something which looks very, very close to a line with a slope the same as the growth rate that we were looking for. The slope idea and the infinite zoom idea can sort of make an idea of how to get the growth rate at a given point. Let's say that we get a value called a, and then get the point on y equals x squared, where the input is 1 plus a more than 1. The actual slope between the 2 points is equal to 1 plus a squared minus 1 over 1 plus a minus 1. Using the infinite zoom, we know that a must get very close to 0, just above 0, but close enough to be negligible. This might sound odd, as a can technically be dismissed as 0, but is never equal to 0. But this idea is essentially the same as the infinite zoom idea. You know that as you keep zooming, a can never be 0, because if a becomes 0, perfectly 0, then the slope takes the form of 0, 0, which obviously doesn't have a value. This infinite zoom actually has a formal name in mathematics. It's known as limits, and focuses on some value becoming arbitrarily close to a constant. Using limits, we can rewrite the slope. Since we know a is not precisely 0, we can write this and simplify it to just limit a goes to 0, a plus 2. At this point, we can safely ignore the remaining a as 0. Again, this might sound contradictory, but remember that limits in this way are, well, quite different from normal arithmetic. Since the limit goes to 2, we can safely say that the slope at 1, 1 is actually equal to 2. In fact, we can graph this and confirm that the tangent line to the parabola at 1, 1 is y equals 2x minus 1, which obviously has a slope of 2. Okay, so using the idea of limits, you can get the general slope, or the derivative of fx equals x squared for any x value. We can plug in the slope formula and then put a limit on it, and then just simplify it. Note that a, when we're using the limit at this stage, can be safely ignored. We see that the derivative of x squared is 2x. Could you check? Yes. When the x value is 0, the derivative is 0, just as we found earlier on. When x is minus 1 or any negative value, the derivative is always going to be negative, as you saw before. And when x is positive, the derivative is also positive and signals a positive growth rate. The definition of derivatives using limits can be written down with functions in general. F prime x, which signals a derivative of fx, also the same as d over dx of fx, is equal to limit h goes to 0, fx plus h minus fx over h. In this case, h is used instead of a, as it's commonly used in calculus. Remember that f prime x, the derivative, is the rate of change or quote-unquote slope for any given x value. Alright, so let's try plugging in more polynomials. After the third power, it gets pretty tiring to distribute the powers. So let's focus on the ones we got at the point. You can see that the power for a derivative of a polynomial always decreases by 1. For x to the first power, for example, the polynomial has a power of 0. While for x to the third power, the derivative has a power of 2. Furthermore, the coefficients of the derivatives is the same as the power of the original function. For x to the first power, the resulting derivative has a coefficient of 1. For x squared, it's 2. For x cubed, it's 3, and so on. We can extend this new definition for derivatives of polynomials to all polynomials. In fact, with this, we can actually let n equal any number. For example, when the function is x to the half power, or the square root of x, the derivative would be 1/2 times x to the minus 1/2, or this. You can even find a derivative of things like x to the pi, or whatever real number you want. Also, some rules for derivatives here. First, you can add functions together, and the resulting derivative of the new function is the same as the sum of the derivatives of the two original functions. You can think about why this works, but I won't go into detail about it. Second, you can also multiply constants to a function, and the resulting derivative will also have the same constant multiplied to the derivative. You can use this definition of derivatives to find a function when you get the derivative of it. Think about this. What function has a derivative 1? Well, since the derivative of x is 1, we know that the answer to this is x plus a constant. Likewise, we know that a function with a derivative of x is 1/2 of x squared plus a constant. This process of getting the original function using the derivative is known as integrating. The result, or the original function, is the antiderivative. Integrating is thus the opposite of deriving a function. Integrating is useful not just for finding the original function, but also some other useful things, but I won't digress into those. With that said, we can find a formula for integrating a polynomial function. Since the antiderivative of nx to the n minus 1 is x to the n, for x to the n, we know that the antiderivative is 1 over n plus 1 times x to the n plus 1. Except this leads to a problem. What's the antiderivative of 1 over x? Or x to the minus 1? If you plug this into our formula, we quickly get x to the 0 over 0, or 1 over 0. That's obviously not allowed. So is there no function which has the derivative of 1 over x? The answer is no. If you know how the function changes at all moments of time, or just at any given point, we must know the function itself. But this proves to be a challenging task. What kind of function would have 1 over x as the derivative?